Okay, let's just dive right into this. Today, we are unpacking the absolutely incredible mechanics behind modern cloud computing. We're taking a really fascinating journey together. We're going to start high up at the software application layer, checking out how these massive applications actually communicate, and then we're going to travel all the way down into the deep physical infrastructure of the servers themselves. We'll uncover how the cloud engine efficiently shares physical hardware to run the entire digital world as we know it. Let's get started. So here is our roadmap for today. We'll begin with service-oriented architecture, move into REST and SOAP APIs, introduce virtualization, explore virtual machine architectures, and finally, look at the actual mechanisms that make virtualization possible. To really understand the cloud, we have to start with a massive problem. Think about it. In what environment should data center applications actually execute? Historically, you might just give a set of physical Linux machines to each application. But is that good enough today? Not at all. It leads to terrible server underutilization because some applications just don't need a full CPU. We have highly diverse workloads now. Some need more memory, some need more GPU. We absolutely have to share resources to improve efficiency, but we also need incredibly strong isolation between these different apps and users. So, how do we solve this? Well, that brings us to Section 1, Service-Oriented Architecture. This is basically the software solution to those rigid, monolithic applications. Service-oriented architecture, or SOA, is a brilliant architectural pattern. Instead of building one giant, tangled application where everything relies on everything else, application components provide self-contained services to others over a network. A service, in this context, is a well-defined, completely independent unit of functionality. It can be invoked, it performs a specific task, and, crucially, it operates independently of the state of any other services. By breaking apps down like this, the whole ecosystem becomes infinitely more flexible and scalable. Let's break down the key properties of SOA. First, it provides a logical view where services align directly with business needs, like, say, a process order function, completely hiding the underlying code complexity from the user. Second is message orientation. Services interact purely via requests and responses, and that enables loose coupling. It's also platform neutral. Because it relies on standardized formats like XML, it literally doesn't matter what programming language or vendor the underlying system uses. They can all still talk to each other. Think about how this actually plays out in practice. You've got three main roles here. On the bottom right, the service provider creates the service and publishes it. Up at the top, you have the service registry, which acts like a broker. Think of this as a directory or a phone book. The service provider publishes its documentation right to this registry. Then, over on the left, the service requester comes along, searches the registry to find the exact service it needs, and finally binds directly to the provider to execute it. It's this highly organized, distributed dance. So, we have these independent services, but how exactly do they format their messages to one another? That brings us to Section 2, REST and SOAP APIs. Let's start with REST, which stands for Representational State Transfer. It's a remarkably simple architectural style. In Step 1, a client sends a request to a server via a standard web URL using basic HTTP methods. These map perfectly to your standard CRUD operations: create, read, update, and delete, using put, get, post, and delete. In Step 2, the server just responds with the requested resource, most commonly formatted as JSON. It's stateless, meaning each message contains all the info needed to process it, and it's highly cacheable, making it incredibly fast and lightweight. Now contrast that with SOAP, the Simple Object Access Protocol. SOAP is a much stricter, highly standardized messaging protocol. Every single message is wrapped in an XML envelope, and while it typically runs over HTTP, it's actually flexible enough to run over other protocols too, like SMTP or FTP. It's definitely a bit heavier than REST, but it's incredibly robust for enterprise-level communication, where strict, machine-readable formatting is absolutely non-negotiable. So, the million-dollar question, when do you use which? Here's a quick comparison. SOAP is a strict XML-based protocol invoking remote procedure calls operating over various transfer protocols, but its performance is heavier. REST, on the other hand, is an architectural style calling services via URL paths restricted to HTTP, but offering much better performance with lean code, often using JSON. If you need speed and simplicity, you go REST. If you need strict, robust, multi-protocol enterprise messaging, you're probably going to lean towards SOAP. Okay, that covers how the software talks. Let's pull back the curtain and shift gears. Section 3, Introduction to Virtualization. We're moving from the API layer all the way down to the physical servers hosting them. Remember our initial problem?
dedicating a whole physical server to just one app is literally throwing money away. The answer here is virtualization. It's the creation of an efficient, isolated duplicate of a real resource, whether that's a processor, memory, disk, or even a whole network. The brilliant part is that to the program running on it, the virtual duplicate behaves exactly like the real hardware. It allows us to multiplex resources, meaning we can run multiple, entirely isolated virtual machines on a single physical host. This dramatically skyrockets our server utilization. Section 4, Virtual Machine Architectures. How do we actually structure and safely stack these virtual layers? Let's look at the evolution of server architecture here. Starting on the far left, you have your traditional physical machine. Next to it is a Type 1 or bare metal hypervisor. Here, the virtual machine monitor, or VMM, runs directly on the hardware itself. This is highly efficient, and it's what you'll see in enterprise data centers. Then, in the third column, we have a Type 2 or hosted VM. Notice how the VMM sits on top of a host operating system. This is what you might be running right now on your personal laptop if you use something like VirtualBox. Section 5. Virtualization Mechanisms. That architecture looks clean conceptually, but what is actually happening inside the CPU? Let's dive deep. To keep things secure, CPUs have these privilege rings. Ring 0 is the highest privilege, the absolute VIP section, usually reserved for the OS. But in a virtualized world, the VMM needs Ring 0, so we use a mechanism called binary translation. The guest OS is intentionally deprivileged and pushed up into Ring 1. When that guest OS tries to execute a sensitive instruction, the VMM catches it, dynamically translates that binary code into safe equivalent instructions, and executes it. And the user apps up in Ring 3, they have no idea this complex translation is happening right below them. But honestly, binary translation can be pretty heavy. So enter paravirtualization. Here, the guest OS is actually modified. It knows it's running in a virtualized environment. Because it knows this, it doesn't just blindly try to execute sensitive instructions. Instead, it issues direct hypercalls straight to the virtualization layer. It completely bypasses the need for that heavy trap and emulate or binary translation process, which results in massive performance gains. Technology evolved again, leading to hardware-assisted virtualization. Modern CPUs literally have built-in support for this now, creating two entirely separate execution modes, root and non-root. The guest OS can now happily run in its normal privilege ring within the non-root mode. When it hits a sensitive instruction, the hardware itself automatically traps it and hands control over to the VMM running in root mode. This hardware-level assist is cleaner, safer, and incredibly efficient. Okay, so it's not just the CPU, right? We have to virtualize memory too. Let's look at Intel's Extended Page Tables, or EPT. Normally, an OS maps a virtual address to a physical address. But in a VM, that physical address is fake. It's just a guest physical address. So we need a two-stage mapping process. The guest OS maps the guest virtual address to the guest physical address, and then the hardware EPT instantly maps that guest physical address all the way down to the true host physical address. By doing this in hardware, we reduce memory management overhead by up to 70%. So we've got the CPU and the memory virtualized. What about the rest? I/O and storage virtualization ensure that our virtual machines can access hard drives and networks without clashing. We decouple storage management entirely from the physical hardware, aggregating multiple physical arrays into massive, centralized virtual storage pools. This is the magic that enables dynamic, on-demand capacity. If your app suddenly needs a terabyte of space, the VMM just carves it out of the virtual pool instantly. No waiting around for someone to install a physical drive. Let's bring this all together. Down at the bottom, you have multiple physical server clusters, but layered over them are virtual clusters. A single virtual cluster can logically group virtual machines that are physically scattered across completely different hardware clusters or even distinct data centers altogether. They are interconnected by a virtual network operating seamlessly as if they were right next to each other. It is an absolute masterpiece of resource management. We have covered a crazy amount of ground today, from SOA and REST APIs shaping the software layer, down through the hypervisors, binary translations, and virtual clusters making the physical hardware sing. But this leaves us with one massive, provocative question to wrap up. With such incredibly deep layers of virtualized hardware and countless open APIs interacting over vast networks, how do we actually secure the cloud? That is exactly what we'll answer next time when we dive deep into cloud security. Thanks for exploring the source material with me today on this explainer.